So last time around, we've seen that there is more to R than just numerical information. In particular, we've seen that R can also represent text or textual information via what we call character strings, and that R can also represent whether something is true or false using logical values. So here's a little table summarizing all that information. And this is the point where I should say that when I talk about the type of some value or the type of some expression, that is actually a technical term that you should be familiar with. When we talk about the type of an expression or a value or a variable, we're designating what is the possible set of values from which it could have come from. So when the type of an expression is numeric, that means it is a number. So examples would include the number 42 or the number 6.7 or the expression cosine of 2 times pi, which evaluates incidentally to 0. Those are all numerical expressions or numerical values. Then when we talk about character strings, we mean textual information, as we learned last time. The way we denote them is by enclosing them in quotes. So hello exclamation mark in quotes would be a character string. Second in quotes would also be a character string. Note, here the number 2 is not treated at all as a number. It's treated as part of text. That is the whole point of character strings. And if we include William Shakespeare in quotes, that is of course also a valid character string. And so are any other textual information that we might enclose in quotes. And finally, we had logical values, and those are a bit special because unlike numeric values and character strings, which can take on a vast number of different values, logical values can only be true or false. There's no other option. And then we've seen that expressions and variables can be any one of these 3 basic types. So what we're going to be doing today is combining these data types into a sequence of values called vectors. So what is a vector? A vector is simply a sequence of values of the same type. That is, a vector comprises of either only numerical or only character string or only logical information. One cannot mix and match them. And the second property is that one can index into these vectors to access their individual entries, which then behave just like any good old value that we've learned about. So for example, if x is a vector that has 10 entries, or as we say, it's a length 10 vector, then x bracket 3, we use these square brackets to access the entries of vectors, would be the third entry of this vector. To define vectors, we use the C function, and really this function is just denoted by the letter C, short for combine different values into one vector. So here's a simple example where we create a character string vector. Let's call it Richard 3 because this is actually the first couple of lines of William Shakespeare's play Richard III. The first entry of it reads, "Now is the winter." The second entry is "of our discontent." Then the third entry is "made." The fourth entry is "glorious summer." And finally, the fifth entry of this vector is "by this son of York." So altogether it reads, "Now is the winter of our discontent, made glorious summer by this son of York." Now we finally reveal one mysterious property of our output that so far made no sense. Now remember in the very first lesson, when we talked about that number 1 that was bracketed at the beginning of every output that R produces, that you can still see at the bottom of the screen in front of "now is the winter." Well, the reason it's there is because those index the entries of a vector. Now, as it happens, so far we've only worked with values and variables that have a single entry, and therefore this number 1 was the only entry that we could talk about. But when we have vectors to consider, then they can have multiple entries, and these bracketed numbers essentially just help us visually to tell which entry of the vector we're talking about. So as you see, what happens in the first line, we have the first 3 entries of the vector: "Now is the winter," "of our discontent," and "made." And then in the next line, we continue with the fourth entry of this vector. That is why you see the number 4 bracketed there. And that entry is glorious summer. And then the final fifth entry is by the son of York written next to it. So as advertised, one can index into vectors and access their individual entries, and those entries will behave just like normal values, in this case just like normal character strings that we are already used to. The way to do that is use this square bracket notation. We write down the name of the variable from which we want to extract something, and then in the square brackets we write down which entry we want to extract. So for example, if we want the third entry of the vector Richard III, then we write down Richard 3 and in square brackets the number 3 for the third entry, and the computer will immediately return the result made, because that was the third entry of this vector. To convince you furthermore that the individual vector entries really are just normal standard character string values, we will show that one can use the usual functions on them. So for example, last time around we learned about the paste function, which takes 2 character strings and merges them into one. So if we apply this paste function to the 2 inputs, which are the third entry of the vector Richard 3 and the fourth entry of the vector Richard 3, then since the third entry, as you can see at the top, was made, and the fourth entry, as you can see at the top, was glorious summer, then when we paste them together, we merge those strings, we end up with the single string made glorious summer. The exact same thing is true of both numeric and logical vectors. They can be defined in the same way using this function called C for combine. So for example, here is a numerical vector that we call numeric vec, and it consists of the numbers 3, 1, 5, 6, 4, 7, and 2. And if we want to access the second entry of this vector, then we just write down numeric vec, and then in the angle brackets, not the angle brackets, in the square brackets, my bad. In the square brackets, we write down the number 2, then that will extract the second entry of this vector, which as you can see at the top is actually 1, because the first entry was a 3 and the second entry was a 1, and the computer duly returns that result. And we can perform operations with the individual entries of the vector as if they were normal values, because that's exactly what they are. They are just normal values. So for example, the fourth entry of the vector divided by the seventh entry of the vector, which you can see immediately returns the result, which is 3. And the reason is that if you look at the vector, the fourth entry is equal to 6, and the seventh entry, which is the final entry in this vector, is equal to 2. So numeric vec 4 divided by numeric vec 7 actually evaluates to 6 divided by 2, which is 3, and that is exactly the result that we see printed on the screen. Finally, just as an example, everything works in the same way with logical vectors, mutatis mutandis. So for example, if we have the logical vector that we call logic vec, and it's equal to true, false, true, true, and we ask for the fourth entry of this vector, then we immediately get back the result true, because the fourth entry in that vector is indeed the value true. Apart from using this C function to create vectors, there are very convenient shorthands for generating regular sequences of numbers. So this is a method that will generate numeric vectors. And in fact, it's not just a method, it's 2 methods that I'm going to be talking about. The first one is using the colon operator. So if we use the colon operator and write down the expression 2 colon 7, what that will do is generate a regular sequence of numbers from 2 to 7 in steps of 1. So as you can see on the screen, if we define a variable called 2 to 7, and assign it the value of 2 colon 7, then this will generate a vector such that its entries are 2, 3, 4, 5, 6, 7. And if we ask for the value of the variable 2 to 7, then indeed it turns out that this is a numeric vector and its entries are exactly as I just said before. The other method is with this seq function, which is short for sequence generation. And it works much like the colon operator, except it is a bit more refined. It gives us a bit more control as for what value we want to start from, what value we want to go to, and what step size we want to go in between those values. So for example, we can generate a vector that starts with the number 0, ends with the number 10, and goes on in steps of 0.5. You can see the output of that on the screen. It's just really a vector going from 0 to 10 in steps of 0.5. So we have 0 and then 0.5 and then 1 and then 1.5, etc. so on and so forth until we reach 10. We've seen that we can index into vectors and we can access their individual entries by using this square bracket notation. But there's more to indexing than that. In particular, it is possible to extract more than one entry from a vector at the same time. And the way to do that is, ironically, to put in the angle brackets not just a single number but a vector of different values. And that vector is then interpreted as the list of indices from which we want to extract values. For example, we have the same numeric vector as we worked with before. And if we want to extract in turn the second, the seventh, and the first entry of this vector, then in the angle brackets we can put in the vector generated with the C function, the vector 2, 7, and 1, so those will stand for the second, seventh, and first entries. And if you look at that vector and follow through carefully, you will notice that the second entry of that vector is 1, the seventh entry happens to be 2, and the first entry of that vector happens to be 3. So what we get back is the vector consisting of the three numbers 1, 2, and 3 in that order, and that is the output that you see on the screen. Similarly, if we want to access the first 3 entries of the vector in that order, then we could say numeric vec, and then in the square brackets we put in 1 colon 3, which by now we know is shorthand for the vector 1, 2, and 3. So we extract the first 3 entries of the vector, which, if you look at the definition, is 3, 1, and 5, and that is exactly what this function returns to us. Next, it is important to know that one can also index vectors with negative numbers. And indexing with negative values will discard the corresponding entries from the vector. So as the simplest example, if we have a numeric vec and in the square bracket we put in -1, that will remove the first entry of the vector. And instead of having 3, 1, 5, 6, 4, 7, 2, as in the definition at the top of the slide, we end up with only 1, 5, 6, 4, 7, 2, as you can see. Similarly, if we want to discard a whole vector of entries, for example, we want to discard the entries 5, 6, and 7, so the last 3 entries in that vector, we can do that. We just put in a minus sign in front of the vector. Notice that I've put parentheses around 5 colon 7. That is because if I didn't put it there, then -5 colon 7 would generate a sequence going from -5 all the way up to +7, and I didn't want to do that. So to override that behavior, I put parentheses around 5 colon 7, so that's what it gets evaluated first. So that is the vector 5, 6, 7, and then we put the -1 in front of those, so it's -5, -6, -7, which means we remove those 3 entries from the vector, and you see that the output matches exactly that. We only have the first 4 entries of the vector, the last 3 have been removed. Now you might be wondering how those functions and operations that we've learned about so far, how they would operate on vectors. And there's a fortunate thing here. The way R has been constructed is that most of the simple built-in operations and functions work entry-wise. To illustrate that, let's define a simple numeric vector called v, and it just consists of the numbers 4, 9, 16, 25, and 36. It doesn't matter, it's just an example. What would happen if we would try to multiply this vector by 2? what will happen is that R will automatically interpret this acting entry-wise. So each individual entry of the vector v will be multiplied by 2, and that's why we end up with 8, which is 4 times 2, and then 18, which is 9 times 2, and then 32, which is 16 times 2, and then 50, which is 25 times 2, and finally 72, that's the final entry, which is 36 times 2. If we take the function square root, that also operates on vectors entry-wise. So if we feed the square root function the vector v, it will take the square root of each of the values, and we end up with the vector 2, 3, 4, 5, 6. Yes, incidentally, the way v was created is that those are squared numbers that were in there initially. So if we take their square roots, then we just get back this nice sequence of numbers. Finally, if we do something like add, or as you see in the bottom of the slide, multiply two vectors together, that is also interpreted entry-wise, as long as the number of entries is the same in both vectors. So for example, let us take the square root of the vector v. You know what that is. It's just above the on the slide. It's 2, 3, 4, 5, 6. We've just talked about that. And we have the vector v, which is at the top of the slide, 4, 9, 16, 25, and 36. And what will happen is these will be multiplied together entry-wise, and therefore we will get 2 times 4, which is 8, 3 times 9, which is 27, and so on and so forth. And this way we will get the result back, which is itself a vector of the same length as the original vectors v and square root v. On top of this, there are also functions that are specific to vectors in the sense that they take a vector of values and then combine them in some way to return a single aggregate result. So let's see a couple of examples. We have the same vector as we had before at the top, the vector v, consisting of the entries 4, 9, 16, 25, and 36. And then we have 8 different functions. All of these functions are built-in functions in R that we have on the slide, so these are useful to know about. Let's go through them one by one. The first one is the sum function, which simply adds up the entries of a vector, clearly. So the sum of v is 90 because 4 plus 9 plus 16 plus 25 plus 36 happens to be 90. The next function is the length function, and the length function returns how many entries a given vector has. So in this case, that is 5, so we get back the result 5. Then we have a function that is called mean, and the mean function computes the arithmetic average, the arithmetic mean, that is why it's called that, of a given set of values. So for example, the mean of v would return the arithmetic average of the values in v, which happens to be 18 in this case. And incidentally, it is exactly the same as if we would have entered the sum of v divided by the length of v, as I indicated in a small comment there. So it's really just a shorthand for that. Next, we have a function that is called median. If you've not heard of medians before, the median value in amongst a set of values is the value such that half the data are larger than that and half the data are smaller than that. So in this particular case, when we have 5 values, it's pretty easy to see just visually that 16 will be the median because exactly 2 values are larger than 16 from this set of 5 and exactly 2 values are smaller. So that will be, in this case, our median. Then, in the second column at the top, you see that there is a function called min and another function called max. Those work much the same way as you would expect them. They stand for minimum and maximum. So min of v returns 4 because the smallest of the entries in the vector v is 4. And max of v returns 36 because that is the largest entry in that vector. Finally, there are 2 functions which collapse into a single number, a measure of how much spread there is in the data altogether. So the first one is the var function, which stands for variance. And if you've never heard about variances or standard deviations, don't worry about this yet. You will learn about them. But if you have, then please be aware that when we calculate the variance of a given set of values, then what we're obtaining is the sample variance and not the population variance. If you need a refresher as for what that means, I've put a little Wikipedia link at the bottom of the slide. You can check it out. Just be aware of that. And then the final function is called SD, which is short for standard deviation, which is simply the square root of the variance. And again, this is sample standard deviation. Again, if you need a refresher, look up the link below. As for what that means, just be aware that that is how this function works. Or if you have not learned about this yet, then do not worry about that just yet. You will have time to worry about that later. The point is, SD of v is just the square root of the variance of the values. So that's it for today. We've familiarized ourselves a little bit with vectors, and we will continue from here next time.